Hey, Mr. Peller, this is Keith Babis,
And Andy Monroe.
and this is us explaining what we have learned about the derivative up to this point.
First, we're going to draw a graph. Then we're just going to make any random function on the graph. There's a function. Then, we're going to pick 2 points on the graph. We're going to call this one A. We're going to call this one B. So, the derivative is the instantaneous velocity, or the instantaneous rate of change. So that means that when B is getting infinitely close to A at a really small value, the tangent line, which is the slope, that is the derivative.
Now that we know what the derivative is, we can use a tangent line equation, which is y equals m times x minus x1, and x1 is just the x value of either a or b, plus y1, and again y is just the y value of a or b. So we know how to get m very easily. We've done that since algebra 2. You use points a and b, and you take the change in y over the change of x. So I'm just going to say a random number, say it's 2. You get 2f from your m value. Then for x1 and y1, you would just plug in one of the points. So say point A is 2, 1. You'd have x minus 2 plus 1. And you would solve that out, and that right there is your tangent line.
So now I'm going to explain how the derivative relates to the function. So I'm going to draw a graph. And this is the function f of x. That's just f. Well, that's just f of x. And we're going to draw the derivative function for this function. f1 of x. So we know which one is which. So the function for this area right here is increasing at a decreasing rate until the slope is 0 at this point. Now, the derivative is coming down towards 0 until at that point it crosses 0. Now, the regular function is decreasing at an increasing rate until it hits its point of inflection right there. And that is when the derivative has a minimum and a slope of 0. And then when the regular function switches concavity, it's now increasing in slope till it hits 0. And that's when the derivative crosses 0, and then they both increase. Now we're going to see how the second derivative relates to the first derivative and the original function. So here is the graph. Here is the first function. Here is its derivative. F1. And here is the second derivative. So, the second derivative relates to the original function in this way. When the original function is concave down, the second derivative is below 0. Below 0. And it's increasing. Now, it's still increasing, and it's above 0 when the function has turned concave up. So at that point of inflection, the second derivative goes from below 0 to above 0. Now it relates to the first derivative when the first derivative is decreasing the second derivative is below 0, and then when it's increasing, the second derivative is above 0. Now that is when the second derivative is concave up. But when it's concave down like that, it would switch the second derivative to look like that.
Munsey just showed how to find the derivative and the second derivative of the function graphically. I'm going to show how to find it in an equation. So here you have your function. But to find the derivative of this, we need to know the power rule, because you have things like x cubed. So the power rule says x to any power, when finding the derivative, you take down the power and it becomes the coefficient, and then you subtract the power by 1, and that is your new power. And also, if there's already a coefficient, like here, you have 3 in front of the x, when bringing down the power, you just multiply it by that coefficient. So the derivative of this function would be, bring down the 3, multiply by the other 3, you have 9x, subtract by 1, squared. Same here. So it would be plus 4x. And then here, the derivative is just 2, because the x goes away. Also again here, 1 does not have any derivative, so it just goes away. And then for f prime, for f double prime, you do the same thing. So it would be 18x plus 4. There are a couple other rules that you need to know when trying to find the derivative. So say you have a function that's x squared times 2x. Well, to do this, you need to use the product rule when you're multiplying a function by another function. So this is f of x, and this is g of x. So it would be f prime of x times g of x plus g prime of x times f of x. So it would just look like this. Take the derivative of x squared, which is 2x, times g of x, which is just 2x, plus the root of 2x, which is 2, times x squared. And that's how you get the derivative. There's also the quotient rule. And the quotient rule is, say you have x squared divided by 2 of x. And to do this, we have a way of remembering it, which is low d high minus high d low all over low squared. So that is just saying that you have the low, so you have the bottom, which is 2x, times the derivative of the high, which is x squared, so you just multiply that, so that's 2x. You subtract it by the high function, x, times the derivative of the bottom, which is just 2. And all that goes over low squared, so it would be 2x squared.
So now that Keith has explained the power rule, product rule, and quotient rule, I'm going to explain the chain rule. So the chain rule is, if you have a function times another function here, and we're looking for the derivative, and I'll just write a function that the chain rule applies to, cos of 3x plus 1. We are going to then take the derivative of f, then what was inside, which is the 3x plus 1, it's the g, times it by its derivative. So that's how the chain rule works. You take the derivative of the outside times the function on the inside times the derivative of the inside. So this would be negative sine, which is the derivative of cos, times the 3x plus 1 times 3, which is the derivative of the inside. So that is a good example of the chain rule. Now we're going to show you a summary of implicit derivatives. So, an implicit equation is an equation that isn't solved for y. So, what are we solving for? Well, we're looking at an equation. So, a good example of equation will be y squared plus sine of x equals 4. So, this equation clearly isn't set up looking to solve for y. So, we're going to take the derivative. So, when you take the derivative of y, you come up with dy dx. So, the 2y will be times dy dx. And then we're going to add cos of x. Now, we're taking the d dx of it, but the d dx of x is dx dx, which is 1, so we don't need to write that. And then that's all going to equal 0 because the derivative of 4 is 0. So now that we're left with this, we can move cos over to the other side, which will get us 2y dy dx equals the cos of x. And then when we're just going to divide that by 2y. And that'll get rid of the 2y. So dy dx will equal cos of x over 2y. Now we're just going to give a brief explanation as to what limits are. So there are 3 rules of continuity. The limit must exist. The limit must exist for all values between a and b. And the limit must equal the function. So, more layman's terms of this, as the function is approaching a point which we'll call c from both sides of x, so from a or b, it must be a real number, it must equal the function, and there can't be a discontinuity. So, if you were to be drawing like a line across the paper, your pen wouldn't be taken off. You would just completely draw through it. So if there's a function, so we'll draw a graph here. And then there's an opening, and then it'll pop up here. Then this would not be a real limit because it's not equaling the function. So that's that. So now we're just going to do a brief explanation of as to what Riemann sums are. Riemann sums are when you have a function and then you're taking points on this function. So bing, 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 points on the function. And then you take the left bounds and they'll make their own little, sorry I drew those weird, but they'll make the, and the right bounds, and they'll make their own little staircase, and we're going to try and calculate the distance under, we're going to calculate the area under them, and that'll be the distance traveled because this is a velocity graph. So, when you put this into your calculator, you'll have your left bound and your right bound, and you'll have your x choice. And then the way to get the best possible answer as to what the total area under it would be is to use as much smaller rectangles under the graph until they're infinitely small.